Okay. Yeah, so welcome to the lecture on nucleic acid structure. Uh, so the reading is Jin Sheng, Essential Bioinformatics, Chapter 16. But there's some material that I give in lecture which is not in the book. So on the exam you can anything that's on my slides is fair game. Um, let's see. So we're going to talk about secondary structure prediction methods, including ab initio approaches, comparative approaches or homology-based approaches. And we're going to talk a little bit about nucleic acid structure in general, and also a little bit about my own research, although that part won't be on the exam. So RNA structure prediction is always behind protein structure prediction, several years behind usually. And the reason it is because it's well, firstly because it's harder, and secondly because there's less resources and less data. And so the reason it's harder is because um, RNA has more atoms per residue. There's more torsion rotatable bonds on the backbone per residue. Its folding is much more intrinsically dependent on charge, uh, and the physics of it are a bit harder than they are for proteins. So their RNA tends to be a bit stickier. It's more prone to getting stuck in kinetic traps. It's got more flexibility, again, because of the size. It tends to be bigger in extent, has longer folding times, and again, it's prone to these kinetic traps. In terms of resources, there are something like 100 times fewer structures of RNA in the protein data bank compared to proteins. There's also something on that order less money being invested in research in RNA, and also there's fewer people working on it. So from all sides, like these are all reasons why RNA structure tends not to progress as fast as protein structure in terms of prediction. So RNA you can find in in multiple forms. So of course you have mRNA, which is the messenger RNA, which is going to get translated into protein, and this can have. You might think of it only carrying information, but actually also it also has structure. There are structures that form, for example, introns, which can be large and complex, and even in the final mature mRNA, there can be secondary structures that form, and that these have an effect on how translation occurs. Then there's ribosomal RNA. So ribosomal RNA refers to the RNA in the ribosome itself, or it's 16S, 23S, or its eukaryotic equivalents. And so the ribosome is quite large and quite well conserved across phyla. So it tends to dominate training sets. It's actually a bit of a problem making sure that your training set is diverse enough, just because the ribosome is the 800-pound gorilla. Then you have tRNAs. So those go into the ribosome, of course, but those are also a somewhat sizable component in terms of structured RNAs in the PDB. You have the introns that I mentioned. So before the mRNA gets exported, it might have some sort of folded RNA sort of fragments that get cleaved out, and then we have a whole zoo of regulatory RNAs. These they're satellite RNA. There's these small nuclear RNAs, small nucleotide RNAs, and so on. It's debatable to what extent structure is important. Many people think it's not important, and uh, there's a lot there's kind of a bit of a dearth of structural information for many of these. And we have other there are other forms, like for example, the RNA occurs in CRISPR and so on. Uh, let's see. So structural hierarchy. So when we speak of primary, secondary, tertiary, quaternary, what we mean is that primary structure just refers to the sequence. So you can have A, U, G, C, C, whatever. If all you know is the sequence, then you know the primary structure. Secondary structure is when you know um, basically where the helices are. So maybe you know like this, where some base pairing is occurring, right? But maybe you don't know the long range contacts. So that's secondary. And then when you have connection between pieces of secondary structure, then you have tertiary structure, right? So maybe you have something that looks like this, where where you know this this helix comes in, and or this loop here makes contact with some receptor, and so on. And quaternary is when you know, for example, let's say you know how these come together. Just hypothetically speaking, that they form some sort of multimer. Okay. And to speak of structure, you have to really have a good sense of what the building blocks are. So, so you should of course know the four canonical residue types. So adenine, guanine, cytosine, thymidine in case of DNA, or uracil in case of RNA. So uracil, you just take off this this methyl group and replace it with just a hydrogen, and then you would have the equivalent that's used that appears in RNA. It's kind of nice to know where all the atoms are, but to be honest, it's not easy to keep track of. Like it's also, most people just look these up when they need them. Okay, so the for the backbone though, I do think you should memorize all the atoms in the backbone, because the numbering is quite logical, and it's good to have a language of nucleic acids so you can discuss structure. So you can start with a phosphorus, and then that's connected to the C5, sorry, the O5 prime, and then that is connected to C5 prime carbon, and then it goes to C4 prime carbon. That's got an O4 prime oxygen. Then you go to C3 prime, C2 prime, C1 prime, and then you close the ring. And then you have an O3 prime oxygen, and that goes to phosphorus, which you'll conventionally consider to be part of the next residue. Then here at the C1 prime, that's where you connect one of these four bases, or maybe a modified base. But anyway, you connect your base there, whichever one it may be. So here, let's just say it's a cytosine. Okay. So you notice that these are just numbered sequentially. So if you start here with C1 prime, that's the one where the glycosidic bond is connected. Then it goes sort of around the ring: C1 prime, C2 prime, C3 prime, C4 prime, C5 prime, right? And so O5 prime is connected to C that doesn't get its own number, just adopts the number of the nearest carbon. This one, you'll just have to remember that it takes the name of this carbon rather than this one. I'm not sure I can tell you why, but anyway, that's why. That's the numbering it gets. In the case of RNA, the C2 prime will have an O2 prime here. And that's the only difference in the backbone. And it's responsible for RNA being stickier and being able to form more tertiary structures than DNA. It's also the reason why RNA can't adopt the B form helix, and we'll talk about that later. Okay, so these are. So I have a plastic model of this nucleic of this ribose. So again, here's the C5 prime, C4 prime, C3 prime, C2 prime, C1 prime, and the O4 prime. And one thing that we don't get into so much in this course is that, but I'll just show you very briefly here, is that there are basically basically just 2 degrees of freedom in terms of the ring conformation. You can have the so-called C2 prime endo like this, which is the dominant form in DNA. It doesn't occur in RNA because this O2 prime, it gets in the way. It clashes against the backbone. That's again the reason why RNA doesn't occur in the B form. RNA is more likely can be found in the A form. That means a C3 prime endo. So the C3 prime is pointing upwards. Okay. Yeah. Okay. Now, as I pointed out, whereas DNA bases are predominantly engaged in Watson-Crick interactions, RNA has a whole lot more that it does. And so Leonsis and Westhoff came up with nomenclature for describing these the various base pairing interactions that these bases can engage in. And so what they came up with was a sort of language where we say, okay, we can, if we look at this, let's see this purine, we can identify 3 sort of edges that it interacts with. So it can use its Watson-Crick edge here. That means that it uses these 3 atoms here are going to be the ones making hydrogen bonding contacts. And it can also use the so-called Hochstein edge. That means it uses this edge, which is the most distal from the ribose. It can form hydrogen bonds there. Or it can use the sugar edge. And that means it can use these atoms here. And the reason it's called sugar edge is because it can involve this 2' hydroxyl, which is, of course, on the sugar ring. Similarly, if you have a pyrimidine, then you can also have a Watson-Crick edge here, right? So these atoms can make a hydrogen bond. You can also have a sugar edge, again, because it involves the 2' hydroxyl. And they gave a different name to this edge, that's distal. Like, don't call it Hochstein edge anymore. But this one is not going to be used quite as often as it would be in the case of purines. So you don't need to worry so much about that. There's one more thing you need to know about this alphabet. So in order to describe a base pairing interaction, like let's say we're looking at this one here, you need 3 things. You need to know which edge it is on base 1, which edge it is on base 2, and the so-called orientation, of which there are 2. There's cis and there's trans. So cis is Latin for on this side of, and trans means on the other side of, right? So so let's look at this base pairing interaction. Here you can see that the atoms that are interacting are these guys here, right? So that's a Watson-Crick interaction, right? Watson-Crick, or Watson-Crick edge on residue 1. On residue 2, it's these atoms. That's also Watson-Crick, right? So this one is also using its Watson-Crick edge. And it's, in this case, it's cis, because it's based on the glycosidic bonds, these guys. And if the glycosidic bonds are, in a sense, both on the same side of the hydrogen bonds, then it's called cis. And if they're on opposite sides of the hydrogen bonds, it's called trans. So here, it's admittedly not immediately obvious, because they're not exactly all clearly and unequivocally on one side. But it helps also to look at what direction they're pointing in. So if you draw an arrow that's kind of pointing toward the ribose in both cases, then these are both pointing in the same direction. So we're going to say cis. We're going to say that they're both on the same side of the hydrogen bonds, right? So sometimes when you're talking about base pairing, you can just use your hands, right? You can say like this: your thumb is the glycosidic bond, and the rest of your hand is the base itself. And so this would be the Watson-Crick edge, and same with this one. So these guys are engaged in a Watson-Crick cis interaction because my thumbs are pointing in the same direction. But they could easily also adopt this interaction. So it's still Watson-Crick, but now it's trans, right? Because you see my thumbs are pointing in opposite directions. Okay. And that's what's happening here. Like you have, again, Watson-Crick and Watson-Crick. And here, these bonds are pointing in opposite directions, right? So Watson-Crick, trans. Yeah, notice that's here we have 3 hydrogen bonds, 2, 3, and here we have 2. Actually, one could argue that maybe one could be formed here. Okay, so let's look at a couple of other examples. So this one, for example, let's just say for the moment that you can't see this, right? Just as an exercise, let's just do it on ourselves. Like you can do it on your own, like cover up these annotations and see if you can identify these interactions. So here, which edge are we using? Right, that's the sugar edge, because it's using, because remember, it involves the ribose. So I'm going to say that's sugar. And here we've got the Watson-Crick edge. So I'm going to call it Watson-Crick. And let's look at the glycosidic bond. So this one's pointing this way. And that one's also pointing this way. So I'm going to call this a Watson-Crick sugar edge cis interaction. Right. And actually, you can rewind the tape and see that this is actually Watson-Crick, this is sugar edge, and this is cis. And Janssen and Westhoff also developed a little symbolic language to represent these, but we're not going to get into that so much. So let's look at this one. Here we've got one where it says, it looks like, well, you're certainly involving the ribose here. It looks like it's actually the O3 prime that's involved this time. But anyway, it's definitely the sugar edge, because it's the ribose that's involved. And then you've got the Hookstein here. And the glycosidic bonds are pointing the same direction, right? So this is Hookstein sugar edge cis. So Hookstein sugar edge trans is one interaction that I've seen a lot in touch loops that we're going to talk about later. Let's do one more. So here we got again the sugar edge, and here you got the involvement of the ribose, so it's also a sugar edge. And you've got these glycosidic bonds that are mostly pointing in the same direction, more than not in any case. So this is sugar edge, cis. Actually, let's just do one more so we can get a trans in. Here we've got sugar edge and Watson-Crick. Right. So I'm going to call this a Watson-Crick sugar edge trans. The reason it's trans, is because, let's see, point the glycosidic bond here, glycosidic bond there. And again, they're not 180 degrees apart, but perhaps you can agree that that they're kind of pointing in opposite directions if you're looking at respect to these hydrogen bonds in the middle, right? Let's just draw a line like that. Okay. At least it's more trans than it is cis. Again, going back to this issue that it's not exactly 180 degrees opposite. Okay, and you can do the other two on your own. So, so what I used the Leonsis-Westhoff nomenclature for back in the day was as a descriptor of RNA structure, and I showed that if you know all the base pairing interactions in your RNA, you can then fold the structures. You have this very terse language for describing structure. However, there was a bit of a shortcoming in that since you don't know anything about the backbone, the degree to which you could recapitulate structure was a bit limited. So a little bit later, I met Bohdan Schneider in the Czech Republic, and he then introduced me later on to Julia Czerny, also in Prague, and they developed this language called nucleotide conformers, or NTCs. And this serves a different purpose. Instead of looking at base pairs, what they're looking at is the backbone conformation of dinucleotides. In other words, pairs of nucleic acid residues that are consecutive in sequence, right? And so they took all they had large data set of dinucleotides. They clustered them, and they found, and then they created names for these different clusters. And of course, as you might imagine, there were two huge clusters, one for A form nucleic acids and another for B form nucleic acids. So A form again is the one that's predominant in RNA, and B form is the one that's DNA prefers the B form. But there are also again other clusters, and so most of the time you can find clusters for whatever dinucleotides you have in your RNA. And it turns out that if you specify not only the base pairs, and let's say in the Leonsis-Westhoff language, but also the NTCs, then you can do a really good job of recapitulating 3D structure. And unfortunately, we haven't gotten that published yet. But I find that the 3D structure is very satisfactory, very similar to the experimental. So what NTCs do is they did the clustering, and they published these torsion angles along the backbone. And we implemented this in MMB, or rather, GD sent his postdoc, Emmanuel Peter, who implemented it in my code, and now we're using it, and it's been worked on quite a bit, so it works pretty fast and efficient, and I found it quite useful. So my code is called MMB, Macromolecule Builder, and it's free and open source. Okay. So an NTC is basically a collection of torsion angles. They also have these distances between these pairs of atoms, basically to compensate for the fact that small inaccuracies in the torsion angles tend to add up and have a bad effect on structure, but this corrects it a bit. Okay. A few words on the A form versus B form that we've been talking about. So Again, most RNA is found in the A form. It cannot form the B form. I'll tell you in a second why. What are some differences, structural differences between the two forms? So the A form, as you can see, it's a bit wider. This diameter is bigger. It's a bit shorter. And something that where you can identify immediately visually is if you look at these base planes, look how they are. You know, they're kind of slanted with respect to the helix axis, whereas for the B form, they're basically perpendicular to the helix axis. They're all parallel. So if you see the base plane kind of stacked like just like a stack of plates, then you've got B form. And if you see that that there's kind of a varying tilt to them, then you've got the A form. So the A form has a deep but narrow major groove. So it's hard for proteins, like for example, transcription factors can't get into this helical form. And the major groove is the one that has more information. Here, the minor groove is wide and quite easy to access, but the minor groove has less information. So it's less easy to interpret what bases are in it if you're looking at the minor groove. And then again, this is the one that's permitted because it has a C3' endo sugar pucker. So it means this thing is pointing in. This atom is pointing upwards, kind of in the direction of the base. If it were B form, then this C2' atom will be pointing up. It would kicks out this O2', and that then would clash with the backbone, right? So that's why RNA can't make the B form again. So in contrast, the B form is the most common form for DNA. DNA could form the A form, but the B is more stable. The helix is again narrower and more elongated in terms, like if we're talking about the same number of bases, it's going to be longer. The major groove is nice and wide and easy to access, so that's why transcription factors can bind in there. And other proteins that need to recognize DNA. So, and it's got quite a narrow minor groove. And again, the base planes are basically almost perpendicular to the helical axis. And again, it's got the C2' endo sugar pucker. Okay, a word about loops. So there are different types of loops. Here, this one is a so-called hairpin loop. And that just means that you have the same strand going up into helix and turning around and then base pairing with itself, right? And so this turnaround is called a hairpin loop, just because it just looks like a hairpin. In here, you can have 3 or more bases. You really can't close this loop very well if you have less than three bases, just because it'll be too tight. There are actually, if you have 4 bases, then you have something called a tetraloop, from Greek word for 4. And that is something that has been quite well studied, and I'll tell you a little bit about what we're doing with them. But for now, suffice it to say that there are certain classes of tetraloops where if you know it's in this class, then you know everything about its 3D structure, because it's a very precisely defined set of non-canonical base pairing interactions in here in the loop. Okay. Then we have bulge loops, and so that means that there's one or more bases that are not base paired, like there's no corresponding base on the other strand, and so they could be bulged in or it could be bulged out, and that has consequences for the interhelical angle. like these helices that come, like if they're bulged out, they can be more parallel. If it's bulged in, then to accommodate the base being inside, the interhelical angle has to be a bit more further from collinear. You can have an interior loop, meaning that one or more residues here are unpaired, and there's a loop correspondingly on the other strand that can have the same or different number of loops. And you can have a multi-branch loop. That means you have 3 or more helices coming together, and you have loops connecting them, and these loops can have any number of residues. Okay. Okay, so let's talk a little bit about secondary structure prediction. So sort of one of the first ways people would try to predict secondary structure was just by making these dot plots. And so they would take a sequence and just ask, what bases in this RNA can make a Watson-Crick interaction with another base in the same strand. So let's say you have an A, so that can base pair with any U's, right? So here are a couple of options, and this A can also base pair with any U's. Where maybe this won't be too close, right? Because only two bases between these two. But let's just put down the dots anyway. So G, and then you have C that can base pair with a G. So here's a few G's. Here's this G, and U can base pair with an A. Here's a couple of A's. Here's this one. And so on. And so the idea was that you can use something called dynamic programming. Depending on which course you're taking this, and you may or may not have seen dynamic programming. SLE, we don't cover it so much. But basically, it means it's a way to trace through this matrix and find consecutive kind of diagonals like this of base paired residues. I mean, you can also use dynamic programming for aligning two separate sequences and finding 2 separate homologous sequences. But anyway, in this case, we're using it to predict the secondary structure. So once you find these diagonals, then you can represent them here in 2D like this. So here we're just saying that that these 4 residues CUGG, these guys, are base paired with these residues over here, CCAG, right? And you notice that these helices are always anti-parallel, so they're always going like this, right? So if the numbers are rising this way, they'll be decreasing this way, right? Okay. But these dot plots are a bit of an oversimplification because you're kind of thinking of them as all base pairs being worth the same, no dependence on what residue types, what order the residue types come in, things like that. So there's some so-called Turner parameters which assign energies to all these interactions. So there's an energy associated with GC, for instance, base pairing, and it's going to be different from the energy that's associated with AU because, as hopefully you recall, GC has 3 hydrogen bonds and AU has 2 hydrogen bonds, right? So there's more benefit to forming a GC than to forming an AU. Okay, but anyway, here you have 4 base pairs, and there's also a certain stacking energy here between consecutive bases, and it matters whether you have a CG or a GC or an AU or UA, right? So there's different numbers for all of these possibilities. Then you have loop closure. So if you have a loop like this, it prefers to be open, because if it's open, then it has lots more degrees of freedom, lots more conformations that are available to it. And you always pay a cost when you reduce degrees of freedom. You get an entropic penalty. That's how rubber bands work. There's no energetic reason why you can't stretch out a rubber band. It's It's an entropic reason. Like it wants to be shorter because that way its chains can be more random. Where the rubber band is stretched, there's just one way for them to be, which is linear. So these when you close the loop again, you're removing basically six degrees of freedom, right? Because you're pinning down one end of it, not only in space but also in angle, right? So because when you force it to join up here, you're also forcing that first bond to point in a certain direction. So loop closure is there's a penalty for loop closure, and it's a higher penalty the longer the loop is. Similarly, there's a benefit to having a free end here, right? So these are two residues that are free and they like it. And actually they would prefer if there were more of them that are free. So the longer this free end is, the more benefit you get. So there's a competition then between sort of entropy and enthalpy in this case, because if let's say hypothetically this were a U and maybe another U, then it would have an enthalpic benefit from base pairing, but an entropic penalty from losing its freedom. So that's why you got to get a little bit of end fraying, because it's not depending on the temperature, they might prefer to be free, or it might be they prefer to be base paired. So to make a long story short, these parameters were all taken into account in something called M-fold, and so then you're able to put not just dots but real sort of energies into your matrix. And when you go back into this dynamic programming, you're doing it on a much more rigorous basis, and you get better results. Right? So it's quite an old method, but it's still kind of effective. It'll eventually, probably soon, get replaced with a machine learning method. But I think it's worth learning about, because it's informed, or it informs you about the physics of RNA folding. Okay, then there's something else you can do, which predict the secondary structure by coevolution. So coevolution basically means that if you have a mutation in one position in your RNA, in order to maintain, if that position is in contact with another position, then the second position also has to mutate in order to maintain that contact. And so you can quantify this sort of communication between residues using information theory. So I think information theory is something that you really need to. I feel like you can really need to know it, because it's useful in so many contexts. It can tell you, for example, how good a translator is. If you have a list of words here in one language and a list of words here in another language, it can quantify how much information was in this document, how much information is in this document, and how much information is shared between them. In other words, how good the translation is. You can use it on an everyday basis. For instance, if somebody tells you, let's say somebody tells you it's raining today, how much is that information worth to you? Well, it depends on the context. Like here in Sweden, if somebody says it's raining, well, maybe half the days in the calendar it's going to rain at some point, and so that information is not worth very much to you. But if you're in, let's say, Lima, Peru, where like a good rain comes along once every 30 years, and they tell you, oh, it's raining outside, well, that's a really significant piece of information. So what Claude Shannon did was, when he invented information theory, was he found certain quantities that allowed him to quantify information. So this log p is the information content. It's the amount of information that you receive when somebody informs you of a certain event. So for example, let's say it's the event of today it's raining. You quantify with log base 2 of the probability of that event. So again, if let's say it's 50% chance that it'll rain today, then this information is only worth log base 2 of 1/2, right? So that turns out to be well, you want the negative of that. So it turns out to be 1 bit, right? Because 2 to the what gives you 1/2. It's 2 to the minus 1, right? So that makes sense, right? If something is 50% likely to happen, then the information of which state it is, it's just one bit. Um, and likewise, if you look at what this logarithm looks like, something that's very unlikely has much more information content. So let's say this was here, 1 bit. This was here when its likelihood is 0.5. But when the likelihood is tiny, let's say rain in Lima, Peru, then this becomes a much more negative number. So much more information. And I'm not going to say how many bits that is, but I mean you can calculate it. But the point is that a rare event, if you know about it, confers much more information than a frequent event. Okay, and then another useful quantity is average information content or information entropy. And that's what you're getting when you take this, right? Because when you take any quantity and multiply it by the probability of that quantity being observed, that's the definition of an average. So here you're averaging over all possible events, right? So in the case of rain, like let's say you average over days of no rain, this probability would be 0.5, and then and this log of the probability would be 1, and on days of where it does rain, then this is the same thing. It's 0.5 times 1. So the total average information of basically just is it raining today is just 1 bit, right? The average information is 1 bit, and Peru would actually give you a lot less information, because even though that one rainy day is very significant, it happens very rarely. So this term is very small, right? So there's a theorem that proves that the better distributed your states are. In other words, the more if all your events are equally likely, that's when you get the highest information entropy. Anyway, so this is information entropy. This is basically the amount of information that you have. Let's say you could in this application, how much information is in one column of your multiple sequence alignment, right? Like if you have in one column, it's A, U, G, C, like kind of randomly distributed. That there's a certain amount of information there, and that's this, right? Information in column 1, information entropy in column 1, or average information in column 1. Then you have a different column that also has a distribution of RNAs. It might be the same sort of average information content, or it might be different. So the key thing that we want here is how much information is shared. This overlap here, right? The overlap can obviously not be bigger than the smaller of these two circles, right? So and the overlap can also be 0. These could be disjoint sets, in which case they're not communicating. So if this overlap is very big, that means that these two positions are communicating, means that there's coevolution. If this intersect is small or even 0, that means that they're not communicating, they're not coevolving, right? And so how do you measure this overlap or this mutual information? So so you use something called the Kullback-Leibler divergence, and in this class we're just going to use this formula, and it's got some interesting properties, but we don't really need to get into it as long as you just know how to use it. So what you're looking at here is the joint probabilities of x and y, and so in this case, you have to get yourself your multiple sequence alignment. So let's say you have your two positions look like this. Like you have A, and you have some bunch of other residues. Then you have a U, and then in another organism you have a U, and then a whole bunch of positions, and then an A, and then a G, and a C, and a G, right? So here you're gonna have to check 4 conditions. First, what's the probability of A, comma U? In this case, that's just 1/4, right? What's the probability of U, comma A? That's also 1/4. And actually, you can see that this is the same for GC and CG, right? These are all the same. Okay. You're also going to need these marginals, the marginal probability of A at position 1, marginal probability of A at position 2, and so on. And in this simple example, these marginals, let's say we do it like this. That's also 1/4, and the marginal of, let's say, U at the other position, that's also 1/4. And these are all going to be 1/4. So you put that 1/4 here, 1/4 here, and then you have the joint probability here outside of the log, and you have to sum over all these possibilities, right? So basically, so you sum over. Let's just start with P of AU. That's 1/4 times a log base 2 of 1/4 over these marginals, which we said were both 1/4. Right? And you have to do this 4 times, right? Because you have AU, UA, GC, and CG, right? Um, so 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 plus plus like that. And so basically this should give you, so here they're communicating perfectly. I think it's kind of obvious, right? Like if you have change here, there's a directly resulting change there, right? And so one of these terms is let's just do it this way: log base 2 of, let's see, we cancel these guys, of 4, and this multiply this whole thing by 4. Log base 2 of 4 is just 2. 2 to the what gives you 4? Well, it's 2. So that's 1/2 times 4. So it's 2 bits, right? And that kind of makes sense because this is there's 4 letters in this alphabet, so you need 2 bits to represent it. And since it's so evenly distributed, the information content in this first column is exactly 2 bits. The information content in the second column is also exactly 2 bits. And then the shared information is also exactly 2 bits. So instead of this thing, circles like that are kind of only partly overlapping, your situation is this ideal one where you have information in the first column, information in the second column, they're completely fully overlapping. So the information column 1, information column 2, and the shared information are all exactly the same. They're 2 bits, like that. Okay. So this is a very simple formula that that you once you know it, you'll find it useful just everywhere. Because it's extremely elegant. It's kind of agnostic to what kind of information you give it. Like let's say you want to connect, for example, wind speed in the Andes to rain in Lima, Peru. Like you could just discretize wind speed in bins from, I don't know, 0 to 10 kilometers, 10 to 20 kilometers, and so on, with rain. And there are different alphabets in these 2 columns, but it doesn't matter. You can see if there's shared information between those 2. Yeah, so again, you can do this at all pairs of positions, right? You can do this. You can calculate mutual information between position 1 and position 2, between position 1 and position, let's say, whatever this is, 6, and position 1 and 7, let's say. And again, where you get high shared information, it's evidence that those 2 residues are in contact. Where it's low, it's less likely they're in contact. Okay, so I want to take a little pause and point out that this is one of the reasons why machine learning for structure prediction is still behind proteins. Yet another reason, shall we say, because coevolution requires good secondary structure alignments, and for proteins you have that. There are lots of proteins where you have thousands, tens of thousands of sequences all quite nicely aligned. In RNA, because your sequences are so because your alphabet is smaller, there's only four residues, it's much easier to misalign. So there's a lot of bad multiple sequence alignments out there, and it's not an easy problem to fix. Like sometimes there can be 2 RNAs that have very similar structure, but their sequence just looks completely different. So it can be hard. Once you do have a good multiple sequence alignment, then this method should work. Okay. Um, so I pointed out that that one way you can predict structure is homology by homology modeling. And so I wrote the first homology modeling method for RNA. And basically, the way this method works is that if you have let's say you have this sequence of unknown structure, and you have structures that known structures that you know to be homologs. In this case, I have two structures. Like this was not quite this tort intron was not quite right because it was lacking some of these touch loop receptor interactions. So I basically patched together a Frankenstein molecule from two different species, and then just put forces that pulled this sequence flexibly onto this rigid sort of chimeric molecule, and then I reported the result. Um, okay, I mean, and the methods have gotten much more sophisticated since then, of course. Um, and like I say, that we're deep into the, no pun intended, the deep learning era, and there's been a lot of progress lately in making deep learning methods that can fold RNAs. I think people are moving away from requiring multiple sequence alignments for the reasons I mentioned. There's a lot more focus on just predicting from single sequences. Um, and so we tried this, and we had we found it was not easy to get the secondary structure right, and so we thought we'd take a different approach and predict these things called motifs. So motifs are small 3D structural elements that are repeated everywhere in RNA, and one of these one of the motifs, as I mentioned, is tetraloops. The tetraloops come in different types. There's some classes that are very structurally defined, for example, the GNRA. And so our idea was that if we could predict the motifs, then we could constrain the secondary and tertiary structure prediction and increase its accuracy. And turns out that you can predict the structure of tetraloops, and you can actually predict it a bit better than you might expect. And the reason is because it's not just what's happening in the tetraloop. As it turns out, what's happening in the stem is also important. For some reason that we haven't quite figured out yet, there are certain base pair types that are preferred here in the stem. That really shouldn't happen because the geometry, or at least the sort of the kind of a bounding box geometry around these base pairs is the same for the different base pairing types. But for some reason, there's a preference. Certain residue types tend to be preferred on the left, and certain other residue types tend to be preferred on the right. And so there's more information there than people used to think. And so we've been exploiting that, and the deep learning method has been learning a bit better than we had expected. And so we're actually doing a fairly reasonable job of predicting tetraloops, and we hope to publish that hopefully this year. And then I've done some more other work on viruses, but I think I'll leave that for a separate video. Okay, with that, I'll end this class.